సార్ ఫైన్ ఫైన్ సార్. అదే అక్కడ ప్రిన్సిపాల్‌గా ఉన్నానని విన్నాను. ఎప్పటి నుంచి? Am I audible?
Yes, sir.
హలో. అదే నాదే అది. యాక్చువల్లీ మా బాబు కంప్యూటర్ అది. మా బాబు అది పేరుతో స్టోరీ అది. ఓకే. ఓకే. సరే.
ఇచ్చారు. Sir, good afternoon, sir.
Good afternoon.
Sir, myself, Dr. Ravi, sir. Sir, how are you, sir?
Hello. Fine.
After 2 years, I am seeing you again. Sir.
Okay.
Sir, how is going on? It go to the same online class or offline classes, sir?
Yeah, everything is fine here.
Everything is fine. Thank you, sir. Sir, thank you so much for accepting our request and you came forward and you are taking this session. I think this
No problem.
This session will be very useful to the participant. I am expecting like that. Thank you, sir. Once again, thank you so much, sir. Please, sir.
Thank you.
Madam, please proceed.
Thank you, sir. Good afternoon, everyone. A warm welcome to Day 7, Session 2 of AICTE sponsored 2-week online FDP on Machine Learning in Image Processing Applications. Good afternoon, all. I would take privilege to introduce today's speaker, Dr. Rafi Ahmed, sir. Dr. Rafi Ahmed, sir, is a professor at IIT Kharagpur. Sir, area of interest are VLSI architectures for signal processing systems, adaptive signal processing, biomedical signal processing. Sir authored a textbook titled Low Complexity Adaptive Equalization, a block floating point based on approach published by VDM Verloc, Dr. Muller in 2009. He published more than 50 publications in various conferences and journals. Sir, we are delighted to have you in this session, sir. I request Dr. Rafi, sir, to take over the session. Thank you. Sir, please start.
Thank you. Yeah. I'll share the PPT. Is it visible?
Yes, sir. Yes, sir. Screen is visible, sir.
Yeah, welcome to this. Sorry,
Sir, screen is visible,
is
sir.
it? Am I audible?
Yes, sir. Your voice
Screen
is
is not
audible.
visible.
Screen is also visible, sir. It is clear, sir.
Okay, okay. So both audio and video are fine.
Yes, sir. Everything is fine.
Okay, welcome to this session on hardware accelerators for neural networks. Okay. So this is the outline of my presentation. So I'll start with the artificial intelligence, which is actually the main set of all these neural networks and all. Then I'll discuss about the different types of the neural networks. In that, basically the deep neural networks, which is having lot of applications in nowadays real life. And I'll discuss here a bit of hardware solutions for DNN architectures. So you might have, heard about all this algorithmic based architecture, algorithmic based, DNNs. But in this, presentation, I'll show how this hardware can be used to implement the DNNs. Okay, and how to increase the processing speed and all hardware accelerators for DNN. So for that, we'll discuss a technique called distributed thematic based hardware accelerators. So starting with artificial intelligence. So this is actually the father of all these neural networks. Okay. So I'll show a slide where the relation between the AI and the different neural networks will be clear. So artificial neural network, as the name implies, this is the intelligence demonstrated by the machines, unlike the natural intelligence displayed by the humans and animals. Okay. So this artificial neural network is not a new one. So it actually, born in around the 1950s, but that time actually it's not gained much importance. So the reason is actually whatever the algorithm that you are going to develop should have a corresponding hardware architecture. So you have to fabricate IC to that algorithm. Then only that particular algorithm will have the popularity. Okay. So that is why the main motto behind this presentation is. So you might have studied different algorithms, but how to map these algorithms onto architecture and how to fabricate IC to implement all these operations. Because nowadays we cannot carry our computers along with us. Okay, if you want to process, if you want to execute these algorithms, normally we use Python or C language or MATLAB, and we need the computers. Okay, so but you cannot carry our computers nowadays. Everything has to be processed by using smart devices, smartphones. Okay, so in order to process this in real time, these machine learning algorithms or neural algorithms in real time. So we need to compute these algorithms in the hardware rather than the software. So if you have a IC correspond to this algorithm, then you can fix this IC at any point and you can do whatever the application with that particular algorithm. Okay, that is the motto behind this. So the reason for this AI failed in 1950s is the reason was that one only, there was no hardware solutions for this artificial neural network. Okay, so later actually this another version of this artificial neural networks has come into the picture in 1980s, which is called an expert system. So the people who are there at 1980s, you might have heard about these expert systems. So that time that expert system was famous in 1980s. So this is a form of artificial intelligence that simulates the analytical skills of a human expert. So still that has failed because of lack of this hardware architectures. Later, so why this neural networks or machine learning is nowadays popular? This is the main reason behind that one is because of the development of CMOS technology. Nowadays we have the CMOS technology. Earlier we used to have the TTL and DTL, this type of technologies. Okay, but those technologies have a lot of drawbacks, so they cannot, implement for the large data type of things. Okay, now here in very large integration, very large scale integration, VLSI. So because of this CMOS technology, we are able to fabricate lakhs and crores of transistors in a single chip. Okay, this has been developed in 1980s around. So because of this advancement in the VLSI technology, the artificial intelligence has gained again the pace. Okay, nowadays, in many of the applications, we are using this artificial intelligence. So starting from logistics, data mining, medical diagnosis, and many applications like in image processing, we have edge detections, image, identification, image recognition. Lot of applications are there. So as I have told, the success is due to the increasing the computational power. So because of this VLSI technology. Okay. So because this computational power is increased because of this famous law called Moore's law. So Moore's law states that, so for every 2 years, the number of transistors that can be fabricated on a given chip area doubles. So it is what happening till now. Okay. So every 2 years, the number of transistors that we are going to fabricate on a given IC are increasing. Almost it is doubled. So because of this, it is increasing the computational power. So because of that, this AI becomes more popular. Okay. Now we have the faster computers, algorithmic improvements also. Another plus point for improvement of this artificial intelligence. Now coming for this artificial intelligence and this neural networks. So this slide will explain in a better manner the differences between this artificial intelligence, machine learning, deep learning and all. Okay. So artificial intelligence is the main set. Okay. So this artificial intelligence, as I have told, is any technique which enables the computers to mimic the human behavior. So we have to simulate the human brain. Okay. So in that, a subpart is a machine learning. Okay. So this machine learning will enable the ability to learn without being explicitly programmed to do so. Okay. This is a part of artificial intelligence. Again, a part of this machine learning is a deep learning. So this is subset of machine learning, which makes the computations of multi-layer neural networks. So this will be clear if I discuss with each and every aspect of these techniques. Okay. Now, so starting from AI, so nowadays the era is of deep learning. Okay. So basically, deep learning, there are 3 types of the architectures are available. So in that, one is called as a feed forward neural network. As the name implies, the data flows in the forward direction. So the second type of neural network is a recurrent neural network. And the third one is convolutional neural network. Nowadays, this is also having a lot of applications. Okay. I will discuss in brief these techniques in the coming slides. So another version of this RNN is a long short-term memory network, LSTM. Okay. So this is capable of learning long-term dependencies. So because of that, which makes RNN smart and remembering the things that have happened in the past. That is what we require because they are going to deal with the big data. Okay. So coming for this, the differences between the FNNN, RNN, CNN, and LSTM. So before going to that, I'll just first discuss about what is the basic neural network. Okay. So basic neural network consisting of a lot of neurons. Okay. There are interconnected nodes. Okay. So a layer of the input nodes receives, this is the input node, which receives this data, and these are the neurons. There are different layers, and finally we have output layer. Okay. So this each node is called a neuron. So normally this artificial neural network with more than 3 hidden layers is called as deep neural network. Here we have 3 layers, hidden layers. These are the 3 hidden layers. This is input layer, this is output layer, and there are 3 hidden layers. So normally if the hidden layers are more than 3, then that particular artificial neural network is called as a deep neural network. And if I take the structure of each neuron, so each node is a neuron, okay? So which is going to be programmed. So the basic neuron will be of the form of this structure. Okay? This will take the inputs x0 to xn, and it will assign the weights w0 to wn. It will add some bias function. Then finally, there will be some activation function acting upon this value. It will give the output y. So this can be expressed by this mathematical expression. So basically, we have this output of this neuron y of n or y of x is given by sigma of, as n varies from 0 to n minus 1 because you are taking n data points, x of n, w of n plus some bias function. For this function, you are taking the activation function of this total sum of product. Okay. So we can operate this neural network in 2 phases. One is called training, and the second one is called the inference. Inference, once if it is trained, we can use for solving the unknown problems. So the basic step here is the training. If I train this neural network in a better manner, we can use to solve the unknown problems using this neural network. Okay. So these are the different versions of this neural network as I have defined. So in case of feed forward neural network, this is recurrent neural network, LSTM. So in case of feed forward neural network, so this is input layer, data flows in the forward direction. It will not come backward. So you see here the data is flowing in the forward direction. Okay. So this is a simple structure, but so this is having some limitations. So like we not apply on the large data where a lot of dependencies are there with the previous data. Whereas in case of RNN, this is the RNN, this is the input. We are going to update these RNN networks. We are going to recurrently change the weights of this particular network. So and finally, after some iterations, we will take the output. As the name implies, recurrent neural network. So here this previous data is again fed back to the input because of this feedback connection. So this can train any type of the data. And on the other hand, we have LSTM network. So here we have multi-layers. There is input layer, output layer. There are some hidden layers. So each one will be having, this one is actually like this RNN. Okay. So each node can be reprogrammable. So you have a lot of interconnections. Because of this, LSTM is also having a lot of applications. So normally if you want to have this process the large data. So if I feed this large data, if I have this 1000 data values, okay, so it will take a lot of time to process this 1000 data. Okay, so one of the technique to increase the processing of this data is to unfold this one. It's also called as unroll. So unrolling is one of the important technique in machine learning, which increases the speed of the processing. Okay. So in unroll, we are going to basically have, this is some sort of the parallel processing type of system. Okay. So you have this neurons or the nodes. We are going to replicate these nodes. So we have 3 H nodes. Okay. So we are going to feed here T-1 data, T data, T+1 data. This all 3 will be processed at the same time. Okay. So because of this, the processing speed will be more. Okay. So it's one of the important technique in machine learning is unfolding or unrolling. It's normally called as unrolling also. So this actually there is a compromise between the complexity and the processing of the speed of the system. Okay. So if I want to have more speed, I can have more unrolling factor. This is having unrolling factor of 3. So we have 3 H blocks. Okay, 3 data will be processed parallelly. Okay. If I have one more such system, it's a 4 parallel system. Okay. there is a compromise between the complexity. If I increase this number of the nodes, okay, so the unrolling factor, so the complexity increases, but at the same time speed also will increases. So there is a compromise between the speed and the complexity of the system. So another important function in this neuron is, as I have told, this is the activation function. So what are the different activation functions? So there are the activation functions can be, it can have some like something like sigmoid or some tan H function we have. So different activation functions that we are going to discuss in the coming slides. So this basically transforms the neuron input into the output. It's clear from the mathematical expression that I have given earlier. So what are the features of this activation function is? A squashing effect is required. Means it prevents the accelerating growth of the activation levels through the network. Okay. So it's simple to and easy to calculate. So I'll discuss these things with the actual activation functions. So there are three activation functions which are commonly used in many machine learning applications. So one is step function. So this we know already. Okay. The another is a assign function. For t greater than 0, positive plus 1, for t less than 0, minus 1. Okay. And the other one is called sigmoid function. So sigmoid function is also having a lot of applications, but the drawback of this one is it becomes difficult to generate this sigmoid function, whereas the sine and step function can be easily generated. Okay. This is the mathematical expression for the sigmoid function. Phi of x is equal to 1 by 1 plus e raised to the power of minus ax. Okay. Now the question is how to generate this. So this is compared to the other two functions, this sigmoid function is having a lot of advantages. Okay. This is one of the good activation function, but the drawback of this one is this is difficult to design. Okay. So this is the mathematical expression of this one. So in order to design this in the hardware, because especially in hardware, because we are discussing about the real-time applications. In real-time applications, whatever the algorithm is there, you have to fabricate IC correspond to that particular algorithm. Okay. Now, how to generate this e raised to the power of x or e raised to the power of minus x in hardware? It's a difficult task. Normally, this type of functions will be generated using lookup tables. Okay, but in order to efficiently generate this type of the hardware, this type of the functions in hardware, there is one important block which is called as a quadratic. There is an algorithm called quadratic algorithm, which can generate exponential functions, tan functions, sine functions, cos functions easily in a smart way. That is why the name quadratic algorithm is called a simple smart way of computing the trigonometric identities such as cos theta, sin theta. And e raised to the power of minus j theta is nothing but cos theta minus j sin theta. So this is easily generated by using the cos theta and sin theta. Okay. So in order to have this hardware correspond to this one, so a better way to generate this one is using quadratic. The full form of the quadratic is coordinate rotation digital computer. So CO stands for coordinate rotation, DI stands for digital computer. So before going for this quadratic algorithm, this quadratic was basically developed by a mathematician, basically called as Holder, in around 1950s. So the main reason of developing this quadratic algorithm is not to implement the cos theta sin theta, because the Holder was mathematician. Okay, so that time his intention was to find out cos of any arbitrary angle, say cos of some 52. Nowadays we have the calculator. Okay, that time they don't have the calculator, so to compute cos of any arbitrary angle, we know the cos theta, cos 30 degrees, cos 60 degrees and all. If want any arbitrary angle cos 52, we cannot that time. Okay, so he has developed this algorithm. According to this Holder, he has defined a universal angles called alpha k. So which he has defined as tan inverse of 2 raised to the power of minus k. Here k varies from 0 to infinity. So if you substitute this k values 0, 2 raised to the power of 0, which is 1, tan inverse of 1 is 45 degrees. Similarly, alpha 1, if you want, this is tan inverse of 2 raised to the power of minus 1. That comes to a value of 26.5. Okay. Alpha 2 comes to a value of 14. So you can see that alpha 0 is greater than alpha 1 is greater than alpha 2, so on. These are the values of alpha 0, alpha 1, alpha 2, so on. Now, if I take any angle theta, which is between 0 to 90 degrees, so he has proved that any angle theta can be expressed as sum or subtraction of these angles. This is delta I, alpha I. Means this can be this delta I for delta 0 is equal to plus 1, and the delta I for I is not equal to 0. Means delta 1, delta 2, all these values are plus or minus 1. So if you expand this one, this theta will comes to delta 0 is plus 1. So alpha 0 plus or minus alpha 1 plus or minus alpha 2 and so on. So you take this alpha 0, you have to add or subtract this angle, you have to add or subtract this angle, you have to add or subtract this angle. Like that, if you do, after some finite iterations, we will get any theta value. Okay. So if I go up to infinity, we will get 100% accuracy. But in practical hardware, we cannot implement this infinite addition. Okay. So we can truncate to some iterations, some finite iterations. Instead of taking this 0 to infinity, I will take some finite iterations m minus 1. Okay. So we are going to see that after some 5 to 6 iterations itself, you will get a good accuracy. You see here, I have taken an example of 56 degrees theta. Okay. So what is this theta? Is alpha 0 plus or minus alpha 1 plus or minus alpha 2 and so on. This is alpha 0, alpha 1, alpha 2, so on. So alpha 0, first one is plus angle. So the next angle has to be added or subtracted. This can be plus or minus. Okay. So who is going to decide this one is whether this 45 is greater than or less than 56. Because this 45 is less than 56, I will add the next angle. By adding these two, you get a value which is greater than 56. So I have to subtract the next angle. Up to here, a value which is, less than, which is greater than 56. So we have to add, we have to subtract the next angle. Okay. And after this, the sum is less than 56. So you have to add this. Still less than 56, you have to add this. So you see here I have taken only how many iterations? 1, 2, 3, 4, 5, 6. 6 iterations. So after 6 iterations itself, you have got more than 99% accuracy. This is 56.62. The actual value is 56. If you go up to infinity, you will get exactly 56. But even for this 5 or 6 iterations, so this 6 iterations itself have got almost the same value. So that is the motive behind the development of this quadratic algorithm by the mathematician Older. He has shown that any arbitrary angle can be expressed as sum or subtraction of these universal angles. Okay. Now later, that time when the signal processing people, electronic engineers, so they were in search of fabricating the IC corresponding to DFT. So to compute the DFT, they want to fabricate a IC. Because as I have told, any algorithm, if the algorithm wants to popular, so you should need a corresponding hardware architecture. Okay, that time DFT was a very popular algorithm. It was used in many applications. But people are thinking to develop the hardware for DFT. But to develop or to fabricate the IC correspond to DFT, so we need x cos theta, x sin theta type of terms. Because in DFT we will be having fidelity factors e raised to the power of minus j by 2 pi n. So which is nothing but cos theta, sin theta terms. So then the people find this quadratic algorithm. Then they have applied this quadratic algorithm. They have efficiently implemented this x cos x sin theta hardware. Okay. So in order to develop this hardware architecture correspond to x cos theta, x sin theta, which will be useful in the implementation of the activation function in machine learning algorithms. Because the basic neuron will be having activation function. Okay, if you want a neural network or the machine learning algorithm in a hardware, so basically first you have to fabricate a neuron. So machine learning algorithm is nothing but interconnection of different neurons, okay, with some weights. So basically, how to first construct a neuron. So in order to develop neuron, this theory is explaining this quadratic theory. Okay. So basically, here if I go to this elementary mathematics, if I have a vector xy, if I rotate by angle theta, if I resultant vector, if I call as x dash y dash, then what is the relation between this x dash y dash and xy and theta? This is direction cosines. Okay. So this is x dash y dash will be in the form of cos theta minus sin theta cos theta times xy. Okay. That is nothing but x dash is nothing but x cos theta minus y sin theta. Y dash is nothing but x sin theta plus y cos theta. Okay. But if I take the cos theta common outside, you'll get 1 minus tan theta 1 into xy. Okay. So this we'll call as rod theta. Rotation by angle of theta, this hold together. Let us forget about this cos theta for some time because this is some constant. So we can take care about this at the end of the processing. So in order to get this x dash y dash from xy, so we need to multiply this xy coordinates with this matrix which contains 1 minus tan theta 1. But in the previous Holder's definition, what is this tan theta or tan alpha? 2 raised to the power of minus k. So this is a shift operation. In digital terminology, 2 raised to the power of minus k is a shift operation basically. So we can easily implement this using shifters. Okay. So if we want to get this theta, if I add this infinite such alphas, alpha 0 plus or minus alpha 1 so on up to infinity, we get x of theta, as I have discussed with the example in the earlier slide. Okay. So here if I take the finite iterations, I am taking only from 0 to m minus 1. Okay. If I add or subtract, so what will be this expansion? Delta 0 is plus 1. So alpha 0 plus or minus alpha 1 plus or minus alpha 2 so on up to alpha m minus 1. Okay. So whether the remaining angle has to be plus or minus, that depends upon so whether this alpha 0, alpha 1 or the sum of these things are greater than or less than the total theta. Okay. So this basically this total theta is nothing but sum of the micro rotations. Initially we have to rotate by alpha 0 in the positive direction because alpha 0 is delta 0 is 1. Then the next vector. So if I take some vector here with alpha 0 here, okay. So the next vector has to be rotated in this direction or in this direction, depends upon whether this theta is greater than or less than alpha 0. If alpha 0 is less than theta, I will rotate the second vector also in the forward direction, otherwise in the reverse direction. So like that we are going to rotate this xy how many times? M times. Finally after m rotations, we will get the total angle as approximately theta. Okay. That is the logic behind this. So initially I am moving by this alpha 0 angle. Alpha 0 is positive. So this is plus of this one. And then alpha 1, alpha 2, this we are not showing this matrix. Finally alpha m minus 1. So after rotating this by the alpha 0, alpha 1, alpha 2, so on up to alpha m minus 1, the all rotations together is equivalent to the total angle of theta, okay, on the initial vector xy. So this is how to generate this in the hardware. If I take a simple ith block and I minus 1th block, okay. So what we'll do is initially we'll take we have to get the total angle of theta. What we'll do is I'll take the initial vector x y or x0 y0. I'll rotate by angle of alpha 0. I'll get x0 or x1 x2. Okay. So we are calling this as x dash y dash. Okay. So this x dash y dash is total angle, total rotation of these angles by theta, which is equivalent to this m rotations of alpha. Okay. So initially what I'll do is I'll take this xy, I'll rotate by alpha 0 and then alpha 1, alpha 2, so on up to. Okay. So after alpha 0, what will be the value of this resultant vector? If I call this one as x1, y1. What will be that resultant vector if I call this initial vector as x0, y0? After alpha 0 rotation, if I call as x1, y1. So what will be relation in a similar manner? So wherever theta is there, replace with alpha 0. So if I take in general ith block to I plus 1 block to get x1, y1 here using x0, y0, this is alpha 0, alpha 0, alpha 0, alpha 0. So in general, if I take any ith block, this is I plus 1 block and this is ith block. Okay. So what will be the angle in between? So this will be in this form. xi plus 1, yi plus 1 is equal to xi, yi, we have to rotate by alpha I. Is it clear? So this I is equal to 0. What happens? This is x1, y1 from x0, y0. If I is equal to 1, this will be x2, y2 from x1, y1. So like that, you have to get the previous, from the previous vector, you have to get the present vector. This type of the iterations you have to perform m times to get the total angle of theta. So this is alpha I can be plus or minus 1. So this is minus or plus because already minus is there. If this is plus and by outside is minus, so plus into minus minus. If this is minus, outside is plus or minus. Whereas cos of minus alpha is also plus alpha, so that is why there is no plus or minus here. Sin of this is plus or minus. This is minus or plus, this is plus or minus because here already one minus is there. These two are reverse. And if we take this cos alpha outside, then this will be in terms of tan alpha. We know that according to this older, alpha I or alpha k is equal to tan inverse of 2 raised to the power of minus I. Or from this tan alpha is equal to 2 raised to the power of minus I. So if you substitute this tan here, tan values here, and if you multiply with this, let us forget about this cos theta, which is a constant. This we can take care at the end of the final architecture. Okay? If you neglect this now here, for the sake of simplicity, so this tan alpha is nothing but 2 raised to the power of minus I. So this is x of I plus 1 is equal to x of I plus minus or plus 2 raised to the power of minus I. This is minus or plus, okay? Not plus or minus. So minus or plus xi 2 raised to the power of minus I. And what is yi plus 1 is yi plus 1 is equal to xi into this is plus or minus 2 raised to the power of minus I plus yi. Here also there is some mistake. This plus or minus is here and this is plus. Okay? This is clear from here. So now how to obtain this in a hard way is basically to get x of I plus 1. X of I plus 1 is equal to this is x of I. We have to apply here and minus or plus y of I into 2 raised to the power of minus I. So y of I into 2 raised to the power of minus I, this can be plus or minus. This have given as minus. This can be plus or minus, which is going to be decided by this control signal. This is adder oblique subtractor. So if this control signal is 0, this will be addition. If control signal is 1, this will be subtraction. Okay. Similarly, to get yi plus 1, similar type of the arrangement, yi plus 1 is nothing but xi, you have to shift by 2 raised to the power of minus I. Xi, you have to shift by 2 raised to the power of minus I. This can be plus or minus. And then yi is plus yi. If you multiply this row with this column, xi with 2 raised to the power of minus I plus or minus and yi with 1. Okay? This is plus yi. This is yi and this is plus or minus this. So if this is plus, this will be minus. If this is minus, this will be plus. That is why the control signal I have given as directly here and with complement here. Okay? So that using adder oblique subtractors and a shifter, we can obtain xi plus 1 and yi plus 1 from xi and yi. Similarly, now who is going to decide whether this is plus or minus? This is plus or minus. Okay. So this is for that we have to require the theta. Total theta we have to be rotated. So for that this is a small algorithm which implements to find whether this is plus or minus or plus or minus. To find basically the delta. As I have told, delta 0 is plus 1. Delta I for I not equal to 0 is plus or minus 1. So this small algorithm is going to find out this delta. So theta 0, I will start with theta, given theta, total angle of theta through which I have to rotate xi by I. And delta 0 is +1, and I am taking m iterations. Then theta I plus 1, the next theta is equal to previous theta. You have to delta is ±1, you have to add or subtract the next angle. So who is going to decide whether this is add or subtract? I am taking the sine function of this delta I plus 1. This delta I plus 1 is theta I plus 1 sine function. If this is positive, next angle has to be subtracted. If this is negative, next angle has to be added. So this also can be implemented by using another such type of adder subtractor block. So theta I plus 1 is equal to theta I. So this theta suffix I or theta function of I both are same. This I am writing this notation because of simplicity. So theta I and this delta I, we know this delta 0, delta 1, delta 2, all values we have already computed. These are the values of alpha 0, alpha 1, alpha 2, so on. So this alphas you have to give here, it's alpha I. And sine of this theta is going to find out delta. This is going to decide whether this is to be addition or subtraction. So this is the typical ith block which implements this conic operation. If you have m such blocks cascade on together, you take initially x0, y0, theta 0 to generate x1, y1, theta 1 using this arrangement. Then you apply this x1, y1, theta 1 to another such type of block which is called as conic block. It will generate x2, y2, theta 2. Then you give x2, y2, theta 2 to another conic block. It will generate x3, y3, theta 3 and so on. So if I have m such blocks, finally we will get xm, ym, theta m. So this total angles together is called a theta. Okay. So the final structure will be something like this. So the final structure will be this theta is totally, we have this conic. So we have m such blocks inside this, m such blocks. Okay. The initial input is x0, y0, theta 0, and the final output is xm, ym, theta m. Finally, you'll get, so what will be this output? X cos theta minus y sin theta. You have to multiply this with xy. Okay. So this is x. If I multiply with xy, x cos theta minus y sin theta. And if I multiply this row with xy, x sin theta plus y cos theta. So this is going to be generated. So this is one of the very important architecture. If I give the inputs as theta xy, it is going to generate x cos theta minus y sin theta, x sin theta plus y cos theta. So this type of operations is involved in many of these machine learning applications, image processing applications, communication applications, signal processing applications, where we need x cos theta, x sin theta terms. That can be easily implemented by using the cortex, which is basically consisting of simply adder oblique subtractors, shifters, then the inverter. Okay. So this is how we can implement this actuation function, which is there in computation of this. So if I know this actuation function, we can apply this actuation function on this sum of products. Okay. Now the next question is how to implement this sum of products, which is also called as convolution operation or filtering operation. All this will be in the same form. This is x0, w0 plus x1, w1 plus this is called inner product or sum of products. So in order to implement this using hardware, so we have another technique called distributed arithmetic. Okay. So this just background of just only actuation function in hardware. Now we'll discuss how to implement this in the hardware. Okay. If you have this hardware, if you combine this, you will get the complete neuron. If I interconnect these neurons, you will get a machine learning algorithm. Okay. Now, as I have already briefed this, the need of hardware architecture. So here I will give some more details of this need for these hardware solutions, because basically this the topic of your AICTE program is machine learning in image processing applications. Here I have taken some examples of the image processing or video processing. So it is in this video processing or image processing, we are using the high definition photos. So what is meant by high definition? We are going to use more pixels to represent a image. Okay. So if you have the more pixels, so there will be a clarity of the picture. So we can have, so this high definition is defined as a shooting mode on cameras that produces the larger, wider, and clear, crisper images. Okay. But if you want to increase this definition, high definition images, we have to increase the pixels. Basically, this 4K, this is called ultra high definition images. Nowadays, we are using this ultra high definition images in this recent Rio Olympics also, which held some few years back. So the opening and the closing ceremonies, they have shot in ultra HD, even 8K. 4K means, so each frame will be having this many pixels. This is accept ratio, height and width. So we are going to use 4096 pixels along the height. Along the width, we are going to use 2160 pixels. This is the definition of this 4K. 8K means this is into 2. 4096 into 2 again. This is 8K. So because we are going to use the more and more pixels, we have to transmit. So if you want to transmit the image in in case of Rio Olympics, so this opening and closing ceremonies, they have shot in 8K Ultra HD, and they have broadcasted this program. Okay. So in order to transmit this many pixels, okay, so each pixel, if I take 8 bits of the information, so what is the size of the memory or the number of bits that is to be transmitted if you want to store this in the memory? What is the size of the memory required? Is 4096 into 2160 pixels, and each pixel is at least you have to take 8 bits into 8. So that many bits are required to store this particular one frame. And how many frames you are going to send per second, that depends upon again the type of broadcasting system that we are going to use. So for one frame itself, this much memory is taking, and if I want to transmit, we require the larger data rates. If I use the smaller data rates, what happens? If I transmit the one frame now, it will reach the destination after 5 hours or 6 hours. Okay, so that is based off the transmission. That is why. So what is needed here is we need the high throughput. So you have to transmit more bits per second, 1 gigabits per second, say. Okay. So this many, one frame we can send in only a fraction of second. Okay. As a result of that, so the program seems to be a real time. Okay. Even if this broadcasting also, you can find that after I speak, after a small delay, only the receiver will listen. Okay. So that is why actually we need the higher throughputs. This is one of the main feature of this need for hardware solutions. So to meet the higher throughputs, we cannot do using the software. You have to go for the hardware solutions. This is one reason. And second reason is, so nowadays we are using this mobile phones, smartphones. Okay. So this 25 times there is increase in the mobile data traffic over the next 5 years, and video is a must have on the portable device. Nowadays we have lot of videos in our portable devices. So because we are going to use these mobiles for processing of this videos or images, okay, so they will consume more power. As a result of that, the battery life will be reduced. So you have to recharge batteries in a very short time. So to avoid that, we have to design the circuitry which draws low power. So there is a need of low power circuits. Okay. So these low power circuits can be fabricated by using these hardware solutions. Okay. In computers, so they will they will consume more power. Okay. So this is two reason. So in order to transmit the more bits in a faster manner, we require the higher throughputs. And in order to store this large data in the portable devices, we need to design the circuits which draws low power. So now we have this image or video processing and computer vision applications. are used in many biomedical and research related applications. Okay. So in order to process this using central processing units, so normal computers will be having CPUs. Okay. It is not, sufficient to perform this many computations by CPU. So I have to go for the hardware solutions such as FPGAs, or we can use ASICs also, application specific integrated circuits. So we are going to discuss what are the difference between the FPGA and ASICs in the coming slides. Just excuse me. So there are the three possible solutions. Broadly, you can classify as two possible solutions. So one we can call as a CPU or GPU based, which are called the temporal architectures. So the other option for this hardware solutions is FPGA/ASIC. The full form of ASIC is application specific integrated circuit. This type of architectures are called as spatial architectures. Okay. So as I have discussed, the drawback of the CPU, GPUs are, so they are having less computational powers. Okay. Because of that, this will be used for processing the limited data, not for the high data. Okay. So for high data, we have to go for the programmable devices such as FPGA and ASIC. Okay. So you can see here the difference between the architectures of these two. So in case of the temporal architecture, basically you'll be having a processing element. For any process, you have to define an element called processing element. Processing element is basically a hardware block, so which implements a operation which repeatedly occurs. Okay. Like in case of this filtering operation, we have y is equal to x0 h0 plus x1 h1. So multiply and accumulate. So multiply and accumulate operation is repeatedly occurring. So we'll design the processing element as multiply and accumulate unit, MAC unit. So the operation which repeatedly occurs, for that we will define an element called processing element. These are all processing elements. And we are going to have this processing element uniformly throughout the structure. So these are the processing elements. Here also we have the processing elements. The main difference between these two is in this processing elements are not interconnected. They are independent. Whereas here the processing elements are interconnected. Okay. And here the processing element basically will be having computation only, like arithmetic logical operation. Whereas here the processing elements is advanced one. In addition to computation, this also will have some controlling operation as well as some register files. RF is register file. Okay. So if you see this structure is simple, but here this, although this structure is complex, but you see a lot of features like we can have the control and register files also inside. So because of that, this is capable of processing big data efficiently. So there are some differences between this CPUs, GPUs, FPGA and ASIC. So if you see here, nowadays actually NVIDIA is playing an important role for implementation of this machine learning algorithms. Okay. So if you take this years over the years, so the number of CPUs basically used will be very less. Even if we take the latest technology also, it is only 64 CPUs are using. Okay. Whereas if I take the GPUs, we can go up to thousands of the GPUs. So if you use this more number of CPUs or GPUs, we can have the level of parallel processing more. So you can process the data in parallel using this many processors. As a result of that, overall the speed of the processing will be more. So not speed of the processing, you have to use many of these CPUs or GPUs in parallel. How many CPUs or how many GPUs you can operate in the parallel is given in this bar graph. Only 64 CPUs only can connect in the parallel, whereas in this technology we can have thousands of these. So because of that, GPUs are having more applications rather than CPUs. You can see here CPUs, even though they are easily programmable, but because of the less number of the cores, less parallelism, thereby they are least used for the DNN applications. On the other hand, GPUs, because we can go up to 1000 cores, so we can process 1000 data at the same time. As a result of that, they are widely used for DNN training and inference. Now coming for the again this FPGAs and ASICs. So FPGAs are compared to these two, FPGAs are easily programmable. This is actually second type of this architecture, which is temporal architecture. So between these FPGAs and ASICs, FPGAs are easily programmable because the design flow is also simple. But the problem with FPGAs is you cannot optimize for the various requirements. So because we are going to use this already available libraries like lookup tables will be there, flip flops will be there. You have to take this all these things and you have to arrange. Whereas in case of application specific integrated circuits, so suppose if I have the application of say some image edge detection, okay, so I can fabricate IC. So this will be processes only this edge detection algorithms only. If you want to process the other algorithms, it's not possible. Okay. But for this edge detection, this will have the optimum architecture. Okay. So between these two, this is optimum one. ASIC architectures are optimum, whereas FPGAs are not optimum. But this is easy to design. ASIC is somewhat difficult to design. There is a lot of more complex procedure is there to design this ASIC. ASIC design flow is more complex, but production cost is also higher. So normally, if more number of ICs has to be fabricated, we will go for ASIC one. For fewer number of application, fewer number of this FPGA boards, we will go for this type of application. So for large production, we will prefer ASIC. For small production, we will use FPGAs in summary. So now how to speed up the process? Basically, we need to have the more level of parallel processing. So we can use different register files. As I have told, in case of this temporal architectures, inside this PEs, we have some register files also. So we can connect this processing element to the outside. We can have some off-chip memory also. In addition to this on-chip memory registers will have a small memory. We have to interface to outside memory also. Okay. So that we can do this processing in a faster manner. And these are the different types of this hardware accelerators. We can use this activation buffer as well as wait buffer. Basically, we have to implement this function. This is activation buffer, which will store these activation functions, and this is wait buffer. These are waits. This is another sort of this system. So these are the processing elements. So we'll take the data from the RAM. We'll find out using this wait. We'll find out the output, and we'll find out the activation function using this. Then we will operate sigma of this waits into the inputs x into w. That sigma is there. Then we have to add some bias functions also. We can store some bias functions also in register file. Finally, we'll compute the output. We'll store in the output buffer. Through output buffer, it will process to the dynamic RAM. Okay, this is overall processing. So we'll take the data samples from the RAM. We'll multiply with the wait. We'll apply the activation function. We'll find out the output. Then outputs will be stored back to the DRAM. And there are some accelerators. Accelerator means which is going to speed up the processing. So there are some accelerators based on this the number representation of the data also. So the data can be represented in many ways. One is called fixed point representation. Another is called floating point representation. Okay. So normally we'll use floating point representation because of the large dynamic range. If the data varies from say a value of 1 to 1 lakh, so we cannot use the fixed point rotation. So for that we have to go for the floating point with the exponent and mantissa, because the dynamic range is large. Starting with the value of 1 to 1 lakh, dynamic range is called the range from the lowest value to the highest value. So if dynamic range is large, we have to go for the floating point where we'll be having mantissa and exponent. Whereas for dynamic range is less, if small range of data is to be processed, then is the fixed point. Normally for machine learning algorithms, normally it is 32-bit floating point representation, which is called IEEE 741 standard. But people, they have used instead of, because this is more complex. So in case of floating point arithmetic, if I want to add two numbers, a plus b, so a will be having some exponent, some mantissa, b will be having some exponent, some mantissa. So initially you have to compare the exponents of both numbers. So if the larger number is there, so you have to subtract from the larger smaller number, then you have to shift. So a lot of operations are there, just adding the two floating point numbers. Okay, because of that, the more complexity is there. So the level of parallelism will be less in case of floating point number representation. So what the people they have used is, they have used fixed point rotation. And they found that even they have used fixed point representation, okay, so they are reducing the memory and the power, but the accuracy that is going to be extremely less. They have shown that the accuracy reduction, if you use this fixed point representation, is less, which is still, in the allowable range. So you have the different solutions. So recently, actually, we have taken this problem, how to implement the given inner product of thing without multipliers with less complexity and which consumes low power and all. So we found a distributed arithmetic. Distributed arithmetic is one of the efficient architecture which has been used for implementing the filters, okay, transforms since long time. But this distributed arithmetic has not applied in the implementation of the machine learning algorithms. We first took this algorithm, machine learning algorithm, and we have implemented this machine learning algorithm using distributed arithmetic, and we have got one IEEE transaction papers also. So before going for this implementation of the machine learning algorithm using distributed arithmetic, I'll discuss what is meant by distributed arithmetic in the coming slides in detail. So there are some other type of techniques that are available which are analog in nature. So basically we have the multiply and accumulate operation. As you have seen in this, the neuron computation, we have the activation function. We have discussed about the hardware of activation function, which is audit. Then inside that activation function, we have the inner product, x of n into w of n, which is the input into weights. x0 w0 plus x1 w1 plus x2 w2 and so on. That is nothing but inner product, which also can be called as multiply and accumulate. You take 0 initially, you multiply x0 w0, you add to 0, so you get x0 w0. Then you find out x1 w1, you add to the previous value, which is x0 w0. So we'll get x0 w0 plus x1 y1. Then you compute the next value, you multiply, you accumulate with the previous value. So like that, if you accumulate, you will get this filtering operation, or the operation which is there inside this activation function. This can be implemented by using the analog devices also called memory registers. So this is a full form of memory resistor. This is combination of memory and the resistors. Here basically what we are going to do is, if I want to use V1 G1 plus V2 G2, G1 G2 are conductances, so which is the reciprocal of resistance. So if you want to find out this is, if this is I1, if this is I2, the total current is I1 plus I2 according to Kirchhoff law, current law. So what is that I1 into I2? V1, V2 are the voltage and this conductances. So V is equal to Ri, or I is equal to V by R. But 1 by R is called as G, which is conductance. So 1 by R is G, so V1 is G1 plus V2 G2. So to get this inner product, so inside this activation function also we have similar type of the product. There we have x0 w0 plus x1 w1 plus x2 w2 and so on. So if I want to generate this v1 g1 plus v2 g2, this is a simple circuit. This will give v1 g1 here, this will give v2 g2 here. So because of this connection, this will be v1 g1 plus v2 g2. So like that, if you want to have vector by matrix multiplication, because in many of these machine learning operations, so we have this vector by matrix multiplication. So we can take, this is similar type of this arrangement here. So through this D to A converters, So digital data will be converted into actual, unlocked data. So what is this? This value, this is nothing but inner product of this. This is one vector by vector multiplication. Here we have 4 elements with another 4 elements multiplication. So this is nothing but something like if this is V1, V2, V3, V4, and if these currents are I1, I2, I3, I4, G1, G2, G3, G4 are these ones. So this is nothing but this is V1, G1 plus V2, G2 plus V3, G3 plus V4, G4. Okay. Suppose on the same data, if I have the second matrix column, if these values are different, G1, G2s are different. Here, the first row we have G1, G2, G3, G4. If I call here as G1 dash, G2 dash, G3 dash, G4 dash, that product with the same V1, V2, V3, V4 with G1 dash, G2 dash, G3 dash, G2 dash will be available here. So this is nothing but this is one vector, and this is 4 by 4 matrix. We have 4 elements: 1 element, 2 element, 3 element, 4 element. This is another 4 element. This is 4 by 4 matrix, and this is one 4 by 1 vector. So this product can be implemented here. Finally, we can get this addition. So we will get this matrix by vector multiplication. This also you can implement by using the memory store. This has reported in the reference 17. Okay. But here these are having a lot of difficulties, like so designing of A to D, D to A converter, sample hold circuit. This is very difficult task. Nowadays, lot of research is going on even design of A to D and D to A converters also. Then there are some algorithms like fast FIR algorithms has been implemented in this 17 reference. So to implement the convolutional neural network. So convolutional neural network is similar to the other neural networks, but here we will be having an additional layer which is called filter weights. So in addition to the weights of the neurons and the actuation function and bias function, we will be having one more additional function here, which is called as the weights of the filters. Okay? So you have to you have to be aware that there are two types of the weights here. One is called here the filter weight that we are going to use in this between the two layers. We are going to use the filters in convolutional neural network. So whereas other weight is the weight of neuron, and this is the weight of the filters. Okay. So we are going to place the filters between different layers of the convolutional neural network. So how to implement these filters in a faster manner? Okay. Further, there are some algorithms like the fast FIR filter algorithms, where we are going to decompose these signals into even and odd parts. Thereby, we are going to process this. So if I take the simple n-tap FIR filter with n weights, so this output of this filter is nothing but just convolution. So this is the convolution expression. And if we take in Z domain, the convolution becomes multiplication. Okay. And what is the Z transform of this? This is the definition of the Z transforms. So in order to fastly implement this convolution or FIR filter, so one of the technique which has been used in the literature is, in this particular reference especially, they have implemented this in a faster manner by decomposing this given x of n into the even components and odd components. You see here x0, x2, x4, even components, and this is odd components x1, x3, x5, and so on. And they are calling the Z transform of the even components as x0 function of Z square, because all are function of Z square only. This is Z to the power of 0, of course. This is Z to the power of -2, -4, -6, and all. And if I take Z to the power of -1 common here, here also these are also functions of Z to the power of -2, -4, and so on. Okay. So both these are functions of Z square. So we'll call this as x0 suffix 0 stands for this even components, suffix 1 stands for odd component. And this is Z square, Z to the power of -1 is this. So in order to implement this even component Z transform or odd component Z transform, so we are using this architecture. So we can write any Z transform in this manner. So the Z transform of the even indexed sequence plus Z to the power of -1 into Z transform of odd indexed sequence. Similarly, this H also, this is X. H also we can express in the same manner. H of Z is nothing but even indexed Z transform of H of n odd indexed sequence. Similarly, this Y also we can express. Okay. So if I express everything in even and odd components, so the final expression for this Y of Z is this. Y of Z is the even component plus odd component. This is product of X and H. X is also having even components, odd components. H is also having even component, odd components. If you multiply this, finally you will get the even component of the output Y as X0, H0 plus Z to the power of minus 2 X1, H1. Similarly, this one is equal to X0, H1, X1, H0. So this is X0 in Z domain. In time domain, that is called as X of 2k because this is odd even components. So even component will be in the form of X of 2k. K varies from 0 to infinity. If k is 0, X of 0. If k is 1, X of 2. K is 2, X of 4, X of 6, and so on. All even components will be applied here. This is general structure of even signal. And odd signal's general structure is 2k plus 1. So this is X of suffix 1 is the Z transform of the odd sequence. So this multiplication with this one is nothing but this is H0 in Z domain, this is X1. H0, X1. This will be generated here. And here X0 is this one, H1 is generated here. So these two will be added to get Y of 1, which is nothing but in time domain 2k plus 1. So we are interchanging using this Z domain and X domain. Y suffix 1 means Z domain. In time domain, this is odd sequence, Y of 2k plus 1. Y suffix 0 means in Z domain, and in time domain, Y of 2k. So this is Y of 2k plus 1. Y of 2k is nothing but X0, H0 plus Z to the power of minus 2 into X1, H1. So if I take N-tap FAR filter, so this will require n multiplications. This is like n by 2, n by 2, n by 2, n by 2. Because we are using the half of these multiplications. If we take, say, for example, this one. If I take this is N-tap FAR filter. If I is equal to 0, H0, X0, one multiplication, H1, X1, second multiplication, n minus 1. Total, how many multiplications are there here? Total n multiplications are there to compute Y of n. Okay. If I take the total terms, if I take only half of the terms, how many multiplications will be there? Half only. In this half, in this half. So like that, each block in this H requires n by 2 multiplications. This is n by 2, n by 2, n by 2, n by 2. Total are 4 into n by 2, 2n multiplications. Okay. Now, this is conventional technique. We have not applied any, fast implementation. And how many additions? So in the given here, we have to add n numbers. So to add n numbers, n minus 1 additions are required. 1 plus 2 plus 3. We are adding 3 numbers, but 2 additions. So like that, if you want to add n numbers, n minus 1 additions are required. So here we have n minus 1 additions for each. Total this additions for n minus 1. Okay. Whereas for small sub this is n by 2, n by 2. So this is n by 2 minus 1 additions, n by 2 minus 1 additions. So like that here n by 2 minus 1, n by 2 minus 1, n by 2 minus 1, n by 2 minus 1. If you add all together, we will get 2 into n minus 1 additions. Okay. So this is total, we require 2n multiplication, 2 into n minus 1 additions. Now multiplication is one of the most, computationally intensive operation. Okay. So you have to reduce the number of multiplications to increase the processing of or speed of the system. Okay. So in the next realization, we have shown how this number of multiplications will be reduced at the cost of slightly increasing the additions. Because I don't care the number of additions, because one multiplication is equal to nearly 100 or 1000 additions. Okay. So if I reduce one multiplication, it's a great saving in the hardware. So in order to obtain two parallel efficient architecture, so we have kept this y0 as it is. So what is the expression for y0? We have got y0. I'm not writing the functions of z square to avoid the clumsiness. So I'll just write x0 h0 plus z to the power of minus 2 x1 h1. I'll write that as it is. Y0 as it is written. whereas y1 is x0 h1 plus x1 h2, because we want x0 h1, x0 h0 and x1 h1. So we require 4 such blocks, h0 h1 h0 h1. Of course this block and this block is same, but because the input is different, I need a different multiplication. Okay. So what I am going to do is I am going to take some common resources. This is x0 h1 is there, x1 h0 is there. We have 4 combinations. x0 h0 is a different combination. We require n by 2 multiplications. x1 h1 is another combination, n by 2 multiplications. x0 h1 is another combination, x1 h0 is another combination. We have all 4 possible combinations, so each will require n by 2 multiplications. So here in a smart way we are going to do what the simplification is. y1 x0 h1 x1 h0 is there. This I am going to smartly write as h0 plus h1 into x0 plus x1. So what will be this total thing? We will get h0 x0, but which is not there in this y1. In y1 what is there? x0 h1 x1 h0. But if you write in this manner, you are getting 2 additional terms. We are having h0 x1 h1 x1, but in addition to that we have h0 x0 h1 x1. But this, for this we don't need any additional hardware, because this we have already generated to compute this y0. This is h0 x0 is there, h1 x1 is there. Now here how many multiplications are there? If I take as it is this one, I need 2 multiplications. Each multiplication will have n by 2 multiplication inside again. But in a smart way, what I am doing is I am multiplying this. I am increasing the 2 additions here. Okay, h0 plus h1 is single value, x0 h1 is single value. So I use only 1 multiplication. And what about this multiplication? I have already used it here. What about this multiplication? I have already used it. So how many different combinations of multiplications are there now? Only 3 possible combinations. One is h0 x0 h1 x1, and the sum of this h0 plus h1 into x1. So this total, this multiplication requires n by 2 or n by 2 by 1 multiplications. This one requires n by 2 1 multiplication. This will require n by 2 1 multiplication. So total how many multiplications are required now? 3 into n by 2 minus 1. Okay. So which is less than 2 into n by 2 multiplications, 2n multiplications. Here we require n by 2, n by 2, n by 2, n by 2. But now we require only, this is n by 2, n by 2, n by 2, 3 by 2 into n by 2. So this is number of multiplications we are saving, n by 2 multiplications here. Okay. So previously we have 4 such n by 2 multiplications. Now we have only 3 such n by 2 multiplications. So we are saving 1 n by 2 multiplications. So this is clear here. So in this method they have taken a 3 by 3 convolution. So 3 by 3 convolution. So they require, by using the direct direct technique without the simplification, this technique, they require 9 multiplications. Okay. Whereas by using this parallel, this type of the smart structure, we require only 6 multiplications. Okay. Similarly, additions we are increasing slightly. So the number of percentage of the number of multiplexers saved will be almost 1/3 multipliers we are saving. Because this is 3 parallel structure, n is equal to 3. So n is equal to 3. So we have 3 times 3, which is 9 multiplications. Okay. Whereas here, because of this structure, okay, so previously we have to have 4 such blocks. Now we have only 3 blocks, so it is reduced. Similarly, if I go for the 5 by 4 multipliers, 25 multiplications are required in the ordinary structure. So in this efficient structure, we require 15 only. So as the size increases, the percentage of saving is also increasing. But slightly they are increasing some additions, but we don't care because additions are less complex when compared with the multipliers. So this is one of the technique used to, reduce the complexity involved in the FAR filter computation. So coming for this, our proposed method. So one of my BTech project student and one of my research scholar, myself as a group, we have implemented this inner product using distributed arithmetic. So if you not understand this distributed arithmetic, we should understand what is meant by 2's complement number representation. Because the data can be either positive or negative. So you have to use the signed representation for the data received from the any particular application. So a W bit number in signed 2's complement representation will be written in the binary form as this. This is signed bit, MSB bit, binary point, then the remaining W1, W minus 1 are the magnitude bits. And if I want to convert this into decimal, because each bit can be 0 or 1, so this is sign bit minus 1 for the negative number, 0 for the positive number. So this can be, if it is 0, minus 0 plus 0 does not matter. If it is a negative number, this will be 1, so this will be minus 1. And what are the powers of this one? After decimal point, if you want to convert the binary number into decimal number, fractional numbers, you have to multiply with the negative powers of the 2. So this has to be multiplied 2 raised to the power of minus 1. W minus 3 with the 2 raised to the power of minus 2 and so on. The last one will be 2 raised to the power of minus of W minus 1. So you see the form. If I is equal to 1, what happens? AW minus 2. This AW minus 2. This will be multiplied with 2 to the power minus 1. If I is equal to 2, we will get the next bit AW minus 3. That has to be multiplied with 2 raised to the power of minus 2 and so on. So the last one will be for I is equal to W minus 1. This becomes A0. 2 raised to the power of minus of W minus 1. This is how you can write either binary form or decimal form. Any problem? So this AW minus 1 is 0 for positive number, 1 for the negative number. So the range of the number that we can express is this is the range. Okay. If this input data is outside this range, we are going to normalize the numbers to this range. So that you can easily say that here this is the maximum number is 1 minus 2 to the power of minus of W minus 1. Minimum number is minus 1. To get the maximum number will be positive number only. So the first bit is 0, positive number. And for 3 bits, the remaining 2 bits will be 1, 1 to get the maximum number. So if you convert this into the decimal form, so 0 into 2 raised to the power of 0 is 0. This into 2 raised to the power of minus 1. This into 2 raised to the power of minus 2, which is nothing but 1 by 2 plus 1 by 4. 3 by 4, this I can write down as 1 minus 1 by 4. This is 2 raised to the power of minus 2. So W is 3. So this is in the form 1 minus of 2 raised to the power of minus of W minus 1 is W is 3, 2. So this 4 is 2 raised to the power of minus 2. This is the highest value. And the lowest value will be negative number. So this first bit is 1. And lowest value is remaining all zeros. So this is minus 1. So this is the range of the numbers that can be represented by W bit signed 2's complement representation. So initially, before we are doing the processing, you have to ensure that all the data should be within this range. If not, you have to normalize by dividing the numbers with the largest of the number. So basically here we have inside this activation function we have this type of inner product which is called MAC operation. So normally we will write this in the vector form. You have the simplicity instead of writing this much big expression C0 x0 plus C1 x1 plus 1 up to Cn minus 1 xn minus 1. So this is the notation that we are going to use. This bold letter represents normally vector. So the vector in the signal processing terminology or machine learning terminology is n by 1 matrix. N rows are there. This is 1 row, 2 rows, 1 up to n minus 1 rows, 1 column. Okay. This is called as vector. This is also another n by 1 vector. So this vector I am defining as C0, C1, so on. This vector I am defining as x0 to this. C transpose, if I take this row vector, column vector becomes row vector. Okay. And if I multiply these two, this becomes C0, C1, C2, so on up to this is row vector. So C0, x0, C1, x1, you get this expression. This is a simple way to represent this MAC operation using inner product. Now here, if I take this machine learning applications, okay, so the weights weights will be, we are going to assign the weights, fixed weights for the each input. So this C will access the weight for the input, okay, that we are going to represent using n-bit numbers. Whereas the X is the data received from the any application. If it is medical applications, okay, it's value of the pixel value of the MRI or any sort of this image. Okay, each pixel value is nothing but this X. X is a variable. So this X variable we are going to define using scientific complement representation. So this is Xi as you have defined in the previous way. This is sign bit followed by magnitude bits. Okay. And here I am taking the ith element of that X. So that is why I'll get an extra term I comma W minus 1, I comma W minus 2, I comma W minus 3, so on up to I comma 1 comma 0. This I is ith element. I varies from 0 to n minus 1. So this is the binary form and this is decimal form. Substitute this decimal form here. If you keep this C as it is, you will get this is the formulation of MAC using distributed arithmetic. Here we are going to represent Ci as constant, Ci will keep as it is. Xi we are going to represent with this representation. If you substitute this Xi here, Ci into this. So we are defining this C of capital C. This is capital C. In terms of small c, W minus 1 minus j as this, and capital C, W minus 1. Yes, this including this minus sign, the first term. So this entire thing we are defining as capital C of W minus 1. And this bracket term we are representing as C of W minus 1 minus J, but J is not equal to 0. Because J is J equal to 0, this will be same as this. So this will be C of W minus 1 plus this entire thing is C of W minus 1 minus J raised to the power of minus J. So if I substitute this J is equal to 0 here, in this case, W minus 1 minus J, the limits are actually J is equal to 1 to W minus 1. You see here, limits are J is equal to 1 to W minus 1. The same thing is there. So when J is equal to 0, what happens to this value? This is CW minus 1 to raised to the power of 0 is 1. So this is nothing but this value. That is why I am taking this also inside this one. And I am taking J is equal to 0 to W minus 1. So this is the form. So this capital C's now, capital C's, or this is the definition of the capital C. If I know this capital C's values, then if I expand this one, this is shift add, shift add, shift add only. There is no multiplier is required. So this will be better understand if I take some example. So here I have taken example of, I have taken n is equal to 4, and W is equal to 8. So this will be in the form of, I will be in the form of I is equal to 0 to n minus 1, which is 3, this is 4, Ci xi, this is C0 x0 plus C1 x1 plus C2 x2 plus C3 x3. And what is final y? Y is C of W minus 1 minus J, W I have taken as 8. So this is C7 minus J 2 raised to the power of minus J. Then the comma is there. So y is equal to, expand this one, J is equal to 0, C7 2 raised to the power of 0 plus C6 2 raised to the power of minus 1, and up to C0 2 raised to the power of minus 7. This is the final expression for the y. So on which we are going to apply this actuation function later. That architecture I have already explained. So to obtain the hardware corresponding to this one, capital C's and capital C zeros, this X is nothing but vector X vector is this X vector. I have taken n as 4, so this is x0, x1, x2, x3. And each X we are going to represent by W bits. Here W I have taken as 8, so 8 bits. 7th bit is MSB bit, sign bit, remaining are magnitude bits. Similarly, X1 also 8-bit representation, X2 8-bit representation, X3 8-bit representation. And what is C0, C1, so on up to here we have defined C of W minus 1J is this expression, C of W minus 1 is this expression. So if you expand this C0 will get as this C of I into X of I plus 0. So direct substitution. So if you expand this one, I is equal to 0, C0, X of 0, 0, C1 X of 10, C2 X of 20, C3 X of 30. Means this capital C0 depends upon X of 0, 0, 1, 0, 2, 0, 3, 0. And is this 0, 0, 1, 0, 2, 0, 3, 0. But what are these bits? This can be 0 or 1. So what I am going to do here is, before I am receiving the input, I will take all the possible combinations of the inputs. How many combinations are there here? 4 bits, 16 combinations. So those 16 values I am going to store in read-only memory, a lookup table. This is called lookup table or read-only memory. So if all these bits are 0, 0, 0, 0, what will be this one? Capital C0. This capital C0 is, if you expand this one, small c0 into x of 0, 0 plus a c1 into x of 1, 0, c2 into x of 2, 0, c3 into x of 3, 0. If all these x of 0, 0, 1, 0, 2, 0, 3, 0 are zeros, so 0 into anything is 0, output is 0. Capital C0 is 0. That I will store in the first location. Okay. But if these combinations are 0, 0, 0, 1, if the last bit x of 0, 0 is 1, the remaining all are 1s. If I take this as MSB, this as LSB, then what will be this combination? X of 0, 0 is 1. So what is the corresponding coefficient of x of 0, 0, C0? So C0 into 1 is C0. Remaining C coefficients are 0. So remaining will be 0. That coefficient value is C0. This is 0, 0, 0, 1. The next one is 0, 0, 1, 0. So the next location, actually this is missing. So next location you have to store as C1, because this is 0, 0, 1, 0. The coefficient of 1, 0 is C1. So the coefficient of this is C0, this one is small c1, this one is small c2, small c3. If all are zeros, 0. If it is 0, 0, 0, 1, C0. What is the next combination? 0, 0, 1, 0 means C1. The next combination is C1, that is missing here. So next one is 0, 0, 1, 1, which is 3. So it is C0 plus C1. So what is the last combination? All ones means C0 plus C1 plus C2 plus C3. So this is how we can generate this capital C0 using only read-only memory with 16 locations. Now the thing is, these 4 values is going to decide C0, and the next one, that is 0, 1, 1, 1, 2, 1, 3, 1 is going to decide C1. You can see here, C1 is nothing but I varies from 0 to 3. So this is C0, C1, C2, C3. These values are 0, 1, 1, 1, 2, 1, 3, 1. That is the next column, next row, the previous row of this that I have not shown here. So this is going to decide this. Means by changing this address lines, if I give this address lines as 0, 0, 1, 0, 2, 0, 3, 0, you are getting C0, but the coefficient remains same. If I give the address lines as instead of this 0, 0, 0, 0, if I give 1, 1, 1, 1, you will get C1. If I give 2, 2, 2, 2, I will get C2. 3, 3, 3, 3, I will get C3. Similarly, 6, 6, 6, 6, you will get C6. But for C7, same thing, but negative value is there. Okay. So what you have to do is, for C7, if I give this as 7, 7, 7, 7, I will not get C1. To get C1, what you have to do, whatever the values that I have stored for C0 to C7, C6, I have to take the minus values. Minus is nothing but 2's complement. So what I will do is that for C7, this minus sign I will take care at the end of the architecture. So this is the final architecture which generates this. So this is the combination that I have told. 0, C1, C2, this is C1, C2, C1 plus C2 and so on. This is the final architecture. So what I am going to do is here, total I require 7 clock cycles. You see here, this is total Y is equal to C7 into 2 raised to the power of 0, C6 into 2 raised to the power of -1, so on up to C0 into 2 raised to the power of -7. So to get this complete product, first I will compute C0. Okay. So to compute this C0, what you have to do? You have to give all zeros values here. So in the first clock cycle, I will make this again as 0J, 1J, 2J, so on up to n-1J. Here n-1 is 3 in our case. So if in the first clock cycle, what I will do is J will become 0. So inside this ROM, we have these contents. These contents are stored for all the combinations. So here what will be generated? C0 will be generated. So C0 we have to take direct, or we have to take the 2's complement. This is not even 2's complementer. minus sign. So this minus sign has to be taken only for the C7. Okay, for C0 to C6 plus sign. Okay, so what I will make is S is equal to 1. So I have connected to the 1 only for the last clock cycle. That is fourth clock cycle, not third clock cycle. If I call as 0, 1, 2, 3. Okay, and is 0 for the first 7 clock cycles. For the first 7 clock cycle, this is 0. So this, as it is, this values will be transferred. So here C0 is generated. So initially for the first clock cycle, I will clear this shift register. So this is 0. So here C0 is there, capital C0. So output is C0, that will be available here. So in the second clock cycle, what happens? This capital C0 will go through the right shift. This is nothing but 2 raised to the power of minus 1. So at the second clock cycle, this is C0 into 2 raised to the power of minus 1. And this J is 1. So that C1 is generated here. So what will be added? C1 plus C0 into 2 raised to the power of minus 1. So this C0 initially we have generated. That is, we are after passing through the shifter, it will become C raised to the power of minus 1 in the first shift. So that time I will generate C1 in the next class cycle. So these two will be added. Again, that sum will be passed through the shifter. So this, what will happen? C1 plus C0 to raised to the power of minus 1. If I pass through the shifter, C1 will be shifted by 1 unit. C1 to raised to the power of minus 1. C0 already it has been shifted by 1 unit previously, now another unit. So C0 will be 2 shifts. So after 8 clock cycle, what happens? C0 totally pass through this shifter 7 times, C1 6 times, C2 5 times, C7 it will not pass through this one. That time we will take the final output. So we will get this complete this thing. C0 into 2 raised to the power of minus 7, C7 into 2 raised to the power of 0. It will not pass. But the thing is, when C0 is selected in the last clock cycle, when C0 comes here, because for the C0 the contents should be negative of these contents. That I have to take care at the output. So this multiplexer control signal I will make this as a 1, because this 1 is connected to the 2's complementer. So that whatever the data that we are going to take from this ROM, we will take the 2's complement, that will be available here. So that this will be C7. If I don't take this complement, you will not get minus sign, because in the expression of C7 we have minus sign. Whereas from C0 to C6 we don't have minus sign. Okay? Because this is the definition for C0 to C6. This is definition for C7. In that way, after 8 clock cycle we generate. So you see the complete architecture that we have proposed for this implementation of the inner product, which is available inside this actuation function. Okay. So without multipliers, what is required here? Only ROM, multiplexer, adder, then shifter, delay. This is a very simple circuit compared with the remaining multiplier based architectures. Okay? Because of this, a lot of complexity will be saved. At the same time, the throughput will be increased. Okay? It can process the data in a faster manner. To further increase this speed, so what you have done is, instead of using this a large memory, so n we have taken as 4, so 16 memory locations are required. If I take n is equal to 532, as n increases linearly, the number of ROM sizes increases exponentially. So if the ROM size is more, ROM access time is also more. ROM access time is more, the overall throughput of the system will be decided by the ROM size. Okay. So in order to avoid that the linear exponential relation, so you have to reduce the ROM size. If I reduce the ROM size, memory access time is less. Thereby, I can process the data at the faster rate. So for that, we are using another technique called offset binary coding. So I'm not going into the details of this one. Here, what we are going to do is, if I take these 16 locations, so in the previous case, conventional distributed arithmetic, we have 16 different contents. Whereas here, we have the 16 contents, out of which 8 are this different with plus sign. The remaining half are the same magnitude are same, but the difference is only minus sign. So this minus sign business I will take it at the outside. As the result of that, now I require only half of the memory when compared with the distributed arithmetic, the conventional one. So because of that, this throughput will be more. There will be slight increase in the external hardware. Okay. So this is one technique. Another technique is, instead of using one single big ROM, x0 of j to n minus 1 j. So total we require 2 raised to the power of n locations. What I am doing is this 0 to n minus 1, total n lines, n address lines. I am going to divide into smaller kk lines. How many such kk lines are required? N minus n by k such small ROMs are required. Okay? But each output we have to finally multiply, accumulate using multi-input accumulator. So this also saves the ROM size. As a result of that, the throughput will be more. Okay? So using these techniques, so we have proposed a MVM, is a matrix vector multiplication. As I have told you, this is one of the important operation in LSTM networks. Okay. So this was the basic operation that we have, the matrix by vector multiplication. We have implemented using this vector by vector multiplication I have shown. This is vector by vector multiplication. So if I perform this vector by vector multiplication several times, we'll get matrix by vector multiplication. So this we have implemented using this architecture. This we have proposed in the paper, and we have compared with the existing works. So there are some LSTM networks that are available in the literature, but they're all multiplier based architectures, whereas our architecture is multiplier less architecture. Okay. So as a result of that, we have got a lot of savings in the area. We have saved the area by this much amount. This is our proposed. So this was previously 0.0, 0.3, 0.4 and 0.5, but we got 0.08 in mm square, and power also we have reduced. We have increased the throughput also, and this FPGA implementation also we have done. In FPGA, the number of resources that we have used are less. This we have done for the two different sizes of the layers. We have taken 128 by 128 layer as well as 512 by 512. As the number of size increases, the reduction is more. Okay. So this was the one of the important work that we have performed, and we have published this in this transaction, the second one, which is IEEE transactions on very large integration circuits, the low complexity distributed arithmetic based pipeline architecture for LSTM network. Okay. So I have not gone into these details because teaching in online 2 hours is a difficult task actually. So, and I have one meeting also at 4 o'clock. So I conclude here. If you have any questions, you can ask. Any questions, queries?
Sir, till now there are no queries, sir.
Okay.
I request all the participants
Okay, then
can
thank you.
and ask the queries. I request all the participants to enable the chat box and ask your query. Sir, there are no queries, sir.
Okay, then thank you.
Thank you, sir. Thank you so much. You have shared valuable
Thank you.
information. Many of us doesn't know this concept, sir, but we could understand that clearly. Thank you for giving a thorough insight of the concept. Thank you so
Okay,
much.
thank you. Thank you. Bye.
Thank you, sir. I request all the participants to fill the feedback form come attendance form, which is shared in the chat box. Thank you.